Swayam Prabha. Digital India. Educated India.
Hello, welcome to Module 4, Week 1 of our course on Dynamical Models in Biology. In the last module, we have discussed about using ordinary differential equation to create mathematical model for spread of infectious diseases. In this module, we will continue along that. We will create some new model using ordinary differential equations. So today, in this module, we will try to model growth of a population. Population growth is a very common dynamical process in biology. Population of a city increases with time. Population of animals in a forest increases with time. You may be growing bacteria in a fermenter. Number of bacteria will increase with time. In a tumor, number of cancer cells increase with time. And we want to model that change, that growth in population. Population growth can be complicated. For example, human population growth is a bit complicated with respect to growth of bacteria or growth of tumor cells. May have different processes involved in that. In this module, we will try to create a simplified model to understand how ordinary differential equation can be used to model population growth when the growth of population is very simple, like growth of bacteria in your fermenter, which happen by binary fission. From one cell, you get 2. From 2, you get 4. With some assumption, you can make the model for growth of cancer cells in a tumor like that, because from one cancer cell, 2 cells will be produced. From 2 cells, 4 will be produced, like that. So these are just binary processes, 1 to 2, 2 to 4. And I want to create a mathematical model for that. Remember, we will use ordinary differential equation. And in a dynamical model, the ordinary differential equation represents rate of change. So here, we will write an ordinary differential equation to represent rate of change in the population size. So if I can use a logic that rate of that population growth, I want to measure actually, and obviously this will be proportional to the current population. So if you have more bacteria, obviously the rate will be, effective rate of growth of the bacteria will be higher. So if we represent this proportionality in terms of an ordinary differential equation, I get this equation. Here x represents population of bacteria at time t, that is right now, and r represent a rate constant of growth. So dx dt, that is the time derivative of x, that is rate of change of x, rate of change in population size is equal to r into x. Essentially, dx dt is proportional to x, and we have used r as a proportionality constant. And r is a constant. It is a parameter of this ODE. And x is the dependent variable, t is the independent variable. So if you look into the equation, we have dx dt equal to r into x. Here the power of x is 1, the power of the derivative is also 1. There is no product between x and its derivative. So that means we don't have this product. That means this equation, this ordinary differential equation, is a linear equation. So now, once I have this model, this ODE, which is my mathematical model, we want to ask certain question to this model. So what type of question I can ask? I can ask like this, that I have started with 100 bacteria. I know the rate constant of growth. How many bacteria will be there, suppose after 4 hours? Or I can have a generalized question that I want to know the dynamics of population change. That is, I want to know how with time the X, the population size of the bacteria, will change. So I have this model dx dt equal to Rx. This is my model, and I am asking this question. If you remember what we did in the last module, we essentially integrated this equation, this ordinary differential equation, to generate the function x as a function of time. And once we got that function, we can answer these two questions. So let us here, we'll try to integrate this ordinary differential equation to get this function. How we'll start? Very simple. We'll separate x and time, t. So that's what I have done. I have separated them. So I have to integrate dx by x from x naught to x, and I have to integrate time from 0 to t. So x naught is the population at t equal to 0. X naught is the population when time is equal to 0. So using the general formula, simple formula of integration, dx by x give me ln x, whereas dt by integration give me t. I am integrating from x naught to x and t from 0 to t. So if I simplify, I get ln x minus ln x naught is equal to r into t minus 0, that is equivalent to t. So if I simplify further and rearrange the term, I get ln of x by x naught equal to r into t. Let us do further simplification. Then we get x by x naught equal to exponent e to the power rt. And remember, I want to get x as a function of time, so I want to keep x on one side of the equal to sign and everything else on the other side. So that's what I have done in the next step, and I have rearranged the term algebraically, and I have got x equal to x naught into e to the power rt. If you look into the right hand side of this equation, x naught is a constant because you have decided that is the initial number of population, initial size of the population. R is a rate constant, there is a growth rate constant of growth, and t is the time. So this is my function. Now once I have this function, I want to go back to my first question. So suppose at t equal to 0, my initial population of bacteria is 100. That means I have seeded 100 bacteria in my fermenter. And I know the rate or rate constant for growth is 0.05 per minute. Remember, bacteria grows very fast. So I want to know after 1 hour, t equal to 1 hour, that is 60 minutes, what will be the size of the bacterial population? So how can I answer this question? My model is dx dt equal to Rx. By integrating that with initial condition, I have got x equal to x naught into e to the power rt. So I put the values x equal to x naught e to the power rt. This is x naught for me in this example is 100 into e to the power 0.05 into, remember the time is 60 minutes. Because your r is in minute scale, I have converted 1 hour into 60 minutes. This one I have already done the calculation. This is almost approximately, you can calculate, it is equivalent to 2008 cells. So that means my mathematical model is saying that if I inoculate 100 bacteria and if the growth rate constant is 0.05 per minute, after 1 hour I will get 2008 bacteria. So this is a specific question and specific answer. But suppose I want to get a generalized dynamics, understand the general dynamics of the bacteria. How will I approach it? So my model is dx dt equal to Rx. By integrating, I have got the function x equal to x naught into e to the power rt, and I want to plot this one, so that I want to plot x in the vertical axis and t on the horizontal axis. And that's what I have done here. What I have done, I have taken different values of time from 0 to 240 minutes, that is mean 4 hours, and I have taken a fixed value of x naught, that is 100. Already I know r equal to 0.05 per minute. So using this function, I have got this curve. So see, we have an exponential term here. X equal to x naught into e to the power RT. That means the growth of the population is exponential. And that's what you can see here. We started with 100 bacteria here, just close to 0. And within 3 hours, it has started increasing, and it has started increasing exponentially. By 4 hours, we have reached almost 16 into 10 to the power 6 cells. The huge exponential growth. So, what we have done till now? We have created a ODE-based model for simple growth of bacteria. You may make some assumption, and you can use this type of model for growth of maybe tumor cells also. We ask two questions. One is a specific question, that if I start with a particular number of cells, we know the rate constant for growth, what will be the size of the population after 1 hour or 2 hours? And the second one is, I want to understand the generalized dynamics of population growth, which I have shown here by this plot. Now, isn't there something wrong with this plot? You see, the bacteria are growing exponentially. As we are not considering any death of bacteria, with time, exponentially, this thing will keep on increasing towards infinity. That never happens. If you are growing bacteria in a fermenter or on an agar plate, they don't keep on growing. They, after some time, saturates. They hit a ceiling, after which they don't grow further. That is true for the tumor growth also. That is true for growth of population in a city also. That is true for growth of population of animals in a forest also. The population size cannot keep on increase infinitely. There must be certain limit. So, these limits comes from the crunch of resources. If you are growing bacteria on a plate, after some time there will be no food. There will be no space further to grow the bacteria. If the population of a city increasing, after some time there will be no place for the people to stay. There will be resource crunch for food, job, etc. So population will ultimately plateau and will become stationary. So how can I make this initial model of population growth a bit more realistic to incorporate this idea that the population cannot keep on growing infinitely? I have tried it by creating a very simple model. I tweaked the equation, that ordinary differential equation, to create a new ordinary differential. Here also, your x is the population at time t, r is the rate constant for growth. So dx dt is the derivative, which represents rate of change of your population, is equal to, I have written, r into, obviously, x. In between, I have 1 minus x by k. What is k? K we call carrying capacity. How much bacteria can grow in my agar plate? How much bacteria can grow in my fermenter of 1 liter size? How many people K can stay in a city? So K is the carrying capacity of the environment. So if you look into this equation, what will happen? Initially, when x is much smaller than k, that means the population size is much smaller than k, then 1 minus x by k is almost equivalent to 1. So then my rate equation will become dx dt is equal to r into x, just like my previous equation. So this will give me exponential growth. But after some time what will happen? X will become close to k, or I can write x will start approaching the carrying capacity k. So then x by k will be moving towards 1, and 1 minus x by k will tends towards 0. So my rate of change dx dt will tends towards 0. That means initially I will have growth, exponential growth, but as the population reaches the carrying capacity of the environment, the growth rate will start reducing and eventually it will become 0. This type of equation is called logistic growth equation, and we will call this model logistic model. Now let us go back to questioning this model. If you remember, we can ask two types of questions. We can ask a specific question that I have a particular population right now. What will be the population size after 2 days, 3 days or something, sometime after a specified time? Or we can try to understand the generalized question that what is the generalized dynamics of the population. Now to get this answer, we have to integrate my ordinary differential equation. So this is my ordinary differential equation here in this case. I will try to integrate it. Before integration, I want to rearrange term. So I have rearranged this term. I have multiplied both sides by k. So I get k into dx dt is equal to r into 1 minus x into x. Then remember, I have to separate out x and t. So I have done that. So I have rearranged term here to separate out x and t on both on the other side of the equal to sign. So I get k divided by k minus x into x dx equal to r into dt. I can rearrange this term further. This whole thing k by k minus x into x is nothing but 1 by x plus 1 by k minus x. So from this I get dx by x plus dx by k minus x equal to r into dt. So now we will integrate both sides. So that's what we have here. We integrate dx by x from x naught, that is the initial population size, to the final population x. We integrate dx by k minus x from x naught to x, and we integrate dt from 0 to t. Remember, I have r, it is a rate constant, it is a parameter, it is not changing with time, and I have k, the carrying capacity, which is also a parameter and constant, is not changing with time. So if I use the general formula of integration, from integrating dx by x, I get ln x. Integrating dx by k minus x, I get minus ln k minus x. So I have to integrate from x naught to x, and this one also to be integrated from x naught to x, and time from 0 to t. So by simplification, what I get? I get ln of x minus ln of x naught. This whole thing is coming from this one. From this one I get ln of k minus x plus ln of k minus x naught is equal to RT. I am getting this from this one. So if I simplify further, coupling all those, taking all those logarithmic term together, I get ln of x into 1 minus x naught, k minus x naught divided by x naught into k minus x equal to RT. I will do further rearrangement. I am taking the log out. So I get x into k minus x naught divided by x naught into k minus x is equal to e to the power RT, a exponential term on my right hand side. Remember, I want x as a function of time. So I will keep x on one side of the equal to sign and keep everything else on the other side. So that's what I have done here. Rearrange the term and I get x equal to k, carrying capacity, divided by 1 plus k by x naught minus 1 into e to the power minus RT. You can try this rearrangement yourself. It will be clear and you will see it is very simple rearrangement. So this is the final function that I have got here. X equal to k by 1 plus k by x naught minus 1 into e to the power minus RT. So using this function, I can actually understand the dynamics of the process. So what I started with, I first made a mathematical model in terms of ordinary differential equation. I got the function of a function to represent x in terms of function of time by integrating that equation. And now I want to plot x in the vertical axis, time in the horizontal axis, and that's what I have done here for x naught equal to 100. Just in the earlier example, we started with 100 bacteria. Rate of growth R is, rate constant for growth is 0.05 per minute. Remember, this is rate constant, not rate. K is the carrying capacity. That means 10,000 I have taken. That means my plate or my fermenter can carry or accommodate only 10,000 bacteria. So now if I put this value in this function, I get a curve like this for different values of t. So see here, I have plotted from 0 to 4 hour. This is 4 hour, just like the previous plot. In the previous case, we had, it was exponentially growing like this. That is not happening here. You can see, here in this case, the population is growing, and then after some time, it is saturating at the carrying capacity 10,000. When x is small than k, your rate is higher. So initially you have growth. As t tends to infinity, this becomes smaller and smaller. The whole thing become, the lower denominator become 1, and x reaches towards k, that is the carrying capacity. So what is happening here? We start with 100 cells. Initially it increases exponentially. As it reaches towards the carrying capacity k, it becomes shallower, shallower, and then it becomes flat and hits the ceiling, the saturation point of 10,000. There is no further growth of the bacteria. So if I jot down what we learned from these two exercises, remember I started with the simplest model, the model of growth of bacteria without any bound. I have not considered death, I have not considered any constraint from the environment on the population, and we got exponential growth. We have used an ordinary differential equation to represent the rate of change of the population size, then integrated that to get the function that represents the population size with respect to time, and then we answered questions. Then we moved into making a bit complex model. So starting with a simple model, then we moved into logistic model, where we have considered that the environment has limited resource to accommodate a population. So we have introduced the concept of carrying capacity and just tweaked our previous equation with small addition here and there to create a new ordinary differential equation. And that ordinary differential equation represents the reality far better than the previous one, because now population cannot grow continuously. After some time, it will reach the carrying capacity of the environment, and the population growth will stabilize and remain fixed at that value. And we have created the ODE, integrated that. After integrating, we have plotted t versus x, the population in change in population with respect to time, and we got a sigmoidal curve. Initially there is increase, faster increase, and then the increase becomes slower and reaches a plateau. So this type of model is called logistic model, and the equation that we use is called logistic equation. You can use this type of logistic equation in other cases also beyond population growth, where the process is constrained by the resources from the environment or other. So initially there will be higher rate of the process, and then it will saturate, and we will get a sigmoidal dynamics with respect to time. That's all for this module. Thank you for watching. We will build new models in future.